Hello, chemistry students. This is a key for the trends of the periodic table due to the electromagnetic force. I thought that it would be valuable for you to hear how I think through problems like this and arrive at the correct answers. Now, before we start, I just wanted to remind you that the electromagnetic force is one of the four fundamental forces of the universe. And I know that you learned about this in your geophysics classes last year. But just as a reminder, the electromagnetic force is the force that causes particles that are oppositely charged to attract each other. And the very same force causes particles that have similar charges to repel. And so we're going to talk a little bit about that in this handout. So the first thing that we're supposed to do is to draw a picture of what each factor is that controls or affects the trends that are on the periodic table. Now you'll remember that the patterns in periods are affected by nuclear charge, and the trends in a family are affected by shielding. So let me draw what I think these would look like. So here's my picture for nuclear charge, and you'll see that at the very top I drew an arrow to show that we are moving across a period from left to right. And notice that my plus signs are changing in size. So on the left, my plus signs are smaller, and on the right, they're larger, because as you move across the period, the atomic number for every element starts to increase by 1. Each time that you move from one square to the next, it goes up by 1. And I used a positive sign because that's the charge of the nucleus. Because remember, a nucleus is comprised of neutral particles called neutrons and positive particles called protons. And so the overall charge of a nucleus is always positive. All right, let's take a look at my picture for electron shielding. My representation for electron shielding shows an arrow off to the side that is moving down, and at the very top we have one ring around a nucleus, and then it moves on to 2 rings, and then it moves on to 3 rings. So as you move down a family, you are increasing the amount of energy levels that are found around the nucleus. And remember, this is indicated also by the period number. So elements that are in period 1, namely hydrogen and helium, have only 1 energy level around the nucleus. Elements that are in period 2, which starts off with lithium and then beryllium, those elements are going to have 2 energy levels around the nucleus. And then if you're in period 3, then all of the elements in period 3 have 3 energy levels around the nucleus. So I just wanted to make sure that you remember that there's a correlation between period number and the number of energy levels that we have around the nucleus. And then, of course, as you go down a family, you're increasing in period number each box that you move to. And so each element is going to have 1 more energy level than the one above it. The more energy levels that are found around the nucleus, the more shielding the atom is said to have. So those are my 2 representations for nuclear charge and electron shielding. So now let's use the above factors. So we're going to use nuclear charge and shielding to determine the following trends, and we need to explain why these trends emerge. So the first one that we're going to talk about is atomic size. And we're going to view atomic size as we move across a period. So look at period 4 to help you with this trend. So if you haven't gotten your Chem Helper out yet, then go ahead and put this on pause and do that now, because it's going to be a lot easier for you to have that visual next to you as we go through these problems. Okay. So number 1 says, how does nuclear charge change as you move from the left of the table to the right? Does it increase in strength or decrease? It's going to increase in strength because atomic numbers are going to increase. So remember, we always have to explain why the trend emerges. So it's not good enough to just put increase or decrease. We have to make sure that we're talking about the why. No, and I just wanted to mention that since we're talking about moving across a period, nuclear charge causes trends in periods. So for all of these in this section, you have to think about nuclear charge and how a bigger nucleus affects atoms. Okay, number 2, how would this impact the electrons in the atom? Would it pull them in closer to the nucleus, or would it be more relaxed and let them out further from the nucleus? Well, if you have a stronger nucleus, it's going to attract the negatively charged electrons more. So it's going to pull them in closer. And that's where the electromagnetic force comes in, right? Opposites attract. If you have a bigger positive charge, it's going to attract negative charge more. Oops. How does electron shielding change as you move from the left of the table to the right? Are there more energy levels being added, or does the number of energy levels or electron shells stay the same? Well, this is one that you should be able to answer right away. As you move across a period, all of those elements have the same amount of rings around the nucleus, so it's going to stay the same. Therefore, how would atomic size change as you move across a period? So basically, if you are increasing nuclear charge, and we already said in a previous answer that bigger nuclei pull electrons in closer, then that means that our atomic size is going to go down. It's going to decrease as we go from left to right. And if you didn't remember that, you could always look at the diagram that we created in class. And again, we're going across a period, so you need to take a look at the top where it says across the period. We're talking about atomic size here. So look at the blue, and what happens to atomic size? It goes down. It's not enough, though, just to know this part, just to know what's on this document. You need to be able to say why. So the reason why is right here. So nuclear charge goes up as you move to the right of the period, and larger nuclei pull electrons closer, making the diameter of the atom smaller. And so that's our answer. Okay, the next section is going to treat atomic size, except now we are looking at moving down a family. And we're going to look at the halogens. Now remember that the halogens are group 7 on your periodic table. And the element that's at the top of the halogens, that's fluorine. So go ahead and find that. So we're going to talk about fluorine, fluorine's family, the halogen family here. Let's pick a different color. And here we go. How does nuclear charge change as you move from the top of the periodic table to the bottom? Does it increase in strength or decrease? Well, again, if we look at our halogens, for instance, fluorine is atomic number 9, which means it has 9 protons. But if we go down the family to, say, chlorine, which is atomic number 17, that means it has 17 protons. And if you go down to bromine, it has 35. So what's going on with nuclear charge as you move from the top of the family to the bottom? It's increasing. So nuclear charge is going to increase because atomic number increases. Number 2, how does electron shielding change as you move from the top of the periodic table to the bottom? Are there more energy levels being added, or does the number of energy levels or electron shells stay the same? Well, let's take a look back at the picture that I just drew. As we go down a family, what is happening to the number of rings around the nucleus? It goes from 1 to 2 to 3. So it's going up, which means that shielding is going to increase. Therefore, how does atomic size change as you move down a family? Once again, let's look at this picture. Which of these atoms appears to be the largest? The one with the most rings, because you have to add a bigger and bigger circle in order to accommodate it. So the more rings you have, the larger the atom is. So as you move down the family, atomic size is going to increase. Now, can we explain why? Sure, I just did. All right, so I didn't think you'd have to watch me type it out, so I just put this on pause and typed it for you. But basically, each subsequent energy level that you add to an atom has to have a larger diameter than the one you drew before it. And so by adding more energy levels, you are increasing the size of the atom. Okay, so that's what's happening with atomic size as you move across a period and down a family. Let's go on to our next trend, which is ionization energy. And look I've got the definition here for you. Ionization energy is the amount of energy needed to remove an electron from an atom in order to make it into an ion. So if it is difficult, so if it's harder to pull the electron away, that means that you need more ionization energy. And conversely, an atom that has a low ionization energy is going to lose electrons easily. So remember that if it's difficult to pull away an electron, ionization energy is high. If it's easy to pull away an electron, ionization energy is low. Okay, so let's talk about across a period first. And we're gonna, you should look at period 5 on your periodic table. And I just want to switch back to show you this. So again, we're going across a period and we're looking at ionization energy at the top one. And so ionization energy is going to increase across the periodic table, but now we just need to figure out why that is. Okay. So how does nuclear charge change as you move from the left of the table to the right? Does it increase in strength or decrease? Well, we answered that in the section above about atomic size. We know that atomic number goes up. So it increases in strength. And so now remember, if you are increasing nuclear charge and you're increasing the strength of the nucleus, that means that atoms with bigger nuclei in a period are going to pull electrons in more tightly. So how does this impact the electrons on the atom? Ooh, I just answered this. Will it pull it in more tighter to the nucleus, or would it be more relaxed and hold on to them more loosely? So my answer here is pull them in tighter. How does shielding change as you move from the left of the table to the right? Are there more energy levels being added, or does the number of energy levels or electron shells stay the same? Well, remember that atoms that are found in the same period have the same number of energy levels. So my answer here is stays the same. Therefore, how would ionization energy change as you move across a period? Well, we already know from our Word document that ionization energy goes up. So we can answer that here, that it increases. And now we have to explain why. Well, since we're comparing elements that are in a period, we need to talk about nuclear charge. So as the nucleus of the atoms increases as you move across a period, they become stronger and they pull electrons in tighter. And if the electrons are held more tightly by the nucleus, they're going to be more difficult to remove. Therefore, atoms that have bigger nuclei have higher ionization energies because it's more difficult to remove electrons from them. Okay, so again, I didn't think you needed to watch me type out that answer, but here is what I came up with. I tried to type it out as succinctly as possible. Nuclear charge increases across a period. Larger nuclei hold on to electrons tightly because they have so many protons that they're able to do that. so they are difficult to pull away. That is, it requires more energy to remove an electron from atoms with larger nuclei in the period. So ionization energy increases as you move across a period. Okay, now let's take a look at ionization energy down a family. So let's go back to our other document here. And as you can see, ionization energy as you move down a family is going to decrease. So keep that in mind as we answer these questions. Number one, how does nuclear charge change as you move from the top of the periodic table to the bottom? Does it increase in strength or decrease? Well, if we're looking at the alkali metals, think about beryllium, which is atomic number 4. And in the same family, a little ways down, you've got calcium, which is atomic number 20. So as you move down the family, your nuclear charge is going up. Now you're probably wondering, well, why are we even talking about nuclear charge when we're talking about a family? Because nuclear charge doesn't really have an effect on trends in families. And if that's what you're thinking, you are absolutely right. Shielding trumps nuclear charge in families. So even though nuclear charge is going up, and I do want you to realize that it does go up as you move down a family, but you also have shielding. And the shielding is just going to negate any power that the nucleus has over its valence electrons. So number 2 says, how does electron shielding change as you move from the top of the periodic table to the bottom? Are there more energy levels being added, or does the number of energy levels stay the same? Well, as you saw in the drawing that I did here, as you move from the top of a family down to the bottom, the number of rings is going up. And so shielding goes up. And that's what's happening here. It increases. So how does this impact the electrons on the atom? Does it cause them to be pulled in tighter to the nucleus, or would it hold on to them more loosely? Well, the answer here is that because you have so many rings as you move down the family, those valence electrons are being pushed further and further and further away from the nucleus. And so the nucleus is not going to be able to hold on to them. So the nucleus is going to hold on to them more loosely at the bottom of the family than it does at the top. Okay, so how does ionization energy change as you move down the family? Once again, let's take a look, and we can see that ionization energy is going to decrease, which means that it's going to be easier to take electrons away from elements at the bottom of the family than it is to take electrons away from the elements at the top. And now we have to craft our explanation. All right, everybody, this is the answer that I created. So can I explain why ionization energy decreases as you go down a family? Well, it's because of shielding. Shielding increases as you move down a family, and the more shielding, the further away from the nucleus the electrons are. So the nucleus can't hold on to these electrons, and they are easy to lose. Therefore, it's going to take less energy to remove electrons from elements that are at the bottom of the family than it is to remove electrons than it is from elements at the top of the family. So ionization energy decreases as you move down the family.